Okay, so I know what some of you are thinking right now, and you're thinking, well, I said I wasn't going to do any counting proofs. Well, this is a very simple enough concept where I think it would be useful to explain it without really getting too much into the proof part, although I might do the simple proof for this since it's a simple induction proof. But in this video, I'm just going to focus on the combinatorial proof. If you don't know what that is, do not worry about it. The logic should be fairly straightforward here. So what we're going to be answering is, why is it that the number of subsets something has is going to be equal to 2 to the power of n? Well, let's just take a set as an example here to show you why. Let's take a set called A and have A contain the elements pi, e, let's use gamma, and maybe the number 31. Right, so A contains these 4 elements, and we know that the total number of subsets A has is going to be 2 to the power of 4, which is just going to be equal to 2 times 2, 4, times 2 is 8, times 2 is 16. So there are 16 total subsets A has. And what do we notice? Well, 4 is going to equal to the number of elements A is always going to have. But why is this? Well, it's because when you look at the number of subsets, a subset either has something or it doesn't. It's a very binary type of logic you have to use. So let's just isolate this to look at just the element pi. A subset that can either have pi or not have pi, right? It's that simple. It can't have both pi and not have pi. So this is going to be an or statement. So what we're going to find here is because a subset can either have pi or not have pi, and because these two scenarios cannot exist at the same time, it means that it's an or statement. So then this means there's only one possibility, there's only one option of it having pi and one option of it not having pi. So the total number of possibilities of a subset having pi is going to be 1 plus 1, which is going to be 2. Once again, because it cannot have both pi and not have pi at the same time, these two have to be an or, which means we have to add the two possibilities. And the possibility of having pi is just 1. There's nothing else to really add to it, and similarly of not having it. Now this logic extends to every other element. You can either have E or not have E, which means that because E cannot both be in something and not be in something, it's kind of like saying Johnny can be both in the kitchen and not in the kitchen. That's just not possible. He either is or isn't there. Same here. E either is or isn't in a subset. So that means E has the possibility of being in a subset, which is 1, or it has the possibility of being not in a subset, which is 1. There's only one way it could be in a subset, and there's only one way it cannot be in a subset. So that means the total number of possibilities is going to be equal to 1 plus 1, which is going to be 2. It's going to be the exact same logic for gamma. You can either have gamma or not have gamma, and because it can't be both at the same time, that means it's an or statement, which means that we're going to add these two possibilities up. Well, how many ways can gamma be in something? Only one way. There's only one way it can be in something, and there's only one way it cannot be in something, right? There's no multiple ways of being in the kitchen. You either are or you aren't, right? So same thing here. We're going to add the 1 for our possibilities, and that's going to be 2. And you're going to find the same with 31. There are 2 possibilities for 31 to be in a subset. And what do we find? Well, now that we know each element has 2 possible ways it can or cannot be in a subset, we need to look at it a little more broadly. We need to ask ourselves, okay, what do we do now? Well, what we notice is in between all of these elements, a subset can either have pi and e or not have pi and e. So what does this mean? This means that a subset having pi does not impact or influence it having another element. So it can have pi or not have pi, and that will not affect it having the number 31. It will not matter. 31 doesn't care whether pi is in it or not. So that means these are going to become and statements over here in between all of these possibilities. I'm just going to put 31 for both of the 31 possibilities. So there we go. So what do we find is we have 2 possible ways that it can either pi can be or not be in a subset. multiplied by two possibilities of gamma being or not being in a subset, multiplied by 2 because either E is or is not in a subset, and again multiplied by 2 because 31 is either in or not in a subset. And they're multiplied, once again, because unlike pi, where it cannot both be in a subset and not be in a subset, when we're broadening our scope and we're looking at two elements, it can be true that pi can be in this and E cannot be in this, or pi can be in the subset and E can also be in the subset. Those can both be true, right? So that's why we have the multiplication sign. What do we find? This is just equal to 2 to the power of 4, which is what we got up here. And that's the sort of logic you use to understand why it's 2 to the power of n and not something like 3 to the power of n, or 4 to the power of n, or 2 plus 3x to the power of n, right? Why is it 2 to the power of n? Well, this 2 comes from the fact that an element either is or isn't in a subset, and then to the power of n because it's how many subsets are, so how many elements are in your subset, and the elements don't care about each other. They can exist while another one does or does not exist. The existence of one does not affect the existence of the others. That's why we multiply all of them. So that's why we say 2 to the power of n is how many subsets of something, of a set there are. Or in other problems, how many subsets there are under a certain condition. So there we go. That's sort of the logic as to why we use 2 to the power of n without really getting too into the woods behind the actual mathematical proof for it.